All right, let's talk about rain. We all think we know what it is, right? Water falls from the sky. Simple. But it's really not that simple. How rain actually forms way up there in the atmosphere, well, it's a tale of two totally different worlds. One is this incredibly delicate, almost magical process, and the other, it's a story of pure brute force. So let me just start with a kind of wild question for you. Think about the last time you got caught in a warm summer rainstorm. Got it? Now, what if I told you that that very same rain almost certainly began its life as a snowstorm? And yeah, believe it or not, the answer is often a resounding yes. To understand why, we've got to go on a little trip. I'm talking miles up into the atmosphere to a place where the familiar rules of water, the ones we all learned in school, start to get, well, really, really weird. So picture this. It's a blazing hot summer day down here on the ground, but those huge, towering storm clouds, their tops stretch way, way up. I mean, up where jets fly. And up there, the temperature can plummet to a mind-boggling minus 50 degrees Celsius. It's in that deep freeze that our first story of how rain is made gets started. Okay, so this brings us to our first method. Let's call it the cold cloud recipe. Now, it's got a fancy scientific name, the Bergeron process, but don't worry about that. Just think of it as a very specific, kind of delicate recipe that hinges on one super strange thing that water can do. And that super strange thing is something called supercooled water. This is wild. It's water that is still a liquid, even when the temperature is way below freezing. It just shouldn't be. And it's super unstable. You know when you hear about ice forming on airplane wings when they fly through clouds? That's what's happening. They're hitting these little liquid bombs of supercooled water that just flash freeze the second they touch something solid. This is our star ingredient. So, for our cold cloud recipe to work its magic, you gotta have these three ingredients all hanging out together in the same cloud. You need some invisible water vapor, of course. You need our star ingredient, those liquid supercooled droplets, and you need just a few little tiny solid ice crystals. All right, so you've got all three ingredients. Now the magic happens. In this weird mix, a quiet little war over moisture kicks off. See, for reasons we're about to get into, the water vapor floating around finds it way easier to latch onto an ice crystal than it does a water droplet. So the ice crystals, they basically start stealing the water vapor right out of the air. And as they get bigger and bigger, the supercooled droplets have to evaporate to put that vapor back. It's a total sacrifice play. The droplets literally disappear so the ice crystals can thrive. And here's the why behind it, the simple physics. Think about the water molecules in a liquid droplet. They're kind of like a loose, disorganized crowd. It's pretty easy for some of them to just wander off and escape into the air. But in an ice crystal? Oh no. They're locked into this super tight, organized formation. It's way harder for them to escape. So, since it's so much easier for vapor to just stick to the ice, well, the ice crystals win this fight for moisture every single time. And this chart right here, this really shows you that imbalance in action. Just look at minus 10 degrees. If the air has just enough moisture to be totally full or saturated for liquid water, that's what 100% relative humidity means. That exact same air is actually super saturated for ice. It's at 110%. It's like it's overfull. And nature just hates that kind of imbalance. So it forces that extra 10% of water vapor to just glom onto the ice crystals, making them grow like crazy. So as these ice crystals grow and start sticking together, they get heavy enough to fall. And what are they? They're snowflakes. And if the air down below the cloud is warm enough, like on a summer day, those snowflakes just melt on their journey down. They reach us as those cool raindrops we feel on our skin. So there you have it. That summer shower really did start as a snowstorm. Pretty cool, right? But wait, that's only half the story. Let's completely switch gears and travel to a different world. We're going to the humid tropics. In these places, the clouds are often way too warm for ice to even think about forming. So rain has to happen in a totally different way, a much more violent way. This isn't about magic. This is a story of brute force collision. The basic rule of this game is super simple. Bigger is faster, and I mean way faster. Just look at the difference on this chart. A typical raindrop falls more than 750 times faster than a tiny little cloud droplet. That's not a small difference. In a warm cloud, that speed gap is everything. The bigger droplets are like cannonballs, just plummeting through the cloud and gobbling up all the smaller, slower-moving droplets in their way. And when I say gobbling up, they have a lot of work to do. Get this, for one droplet to grow into a single raindrop, big enough to actually survive the fall to the ground without just evaporating, it has to crash into and merge with about 1 million other tiny cloud droplets. 1 million. This is pure brute force growth by demolition derby. This quote here explains the physics of it perfectly. Just think of a big falling raindrop as a car speeding down the highway. The air flowing around the car, the slipstream, it pushes all the tiny little bugs out of the way, right? They just get swept aside. Same thing with tiny cloud droplets. But the bigger bugs, the big, heavy ones, they have enough momentum to just plow right through that air and splat. They collide with the car. It's the same idea with bigger cloud droplets. They're the ones that get collected. So this process of colliding and growing, what scientists call collision and coalescence, just keeps on going until the raindrop gets too big for its own good. There's a limit. Once it gets to about 5 millimeters across, it's falling so fast that the air resistance pushing up on it is actually stronger than the force holding the drop together. The drop literally gets flattened out, a little depression forms in the bottom, and then bam! It just explodes, breaking apart into a bunch of smaller droplets. And guess what? Those smaller droplets can now start the whole process all over again. So there you have it, 2 completely different ways to make rain. In the cold clouds, where most of us live, it's this delicate, intricate dance of physics, all starring ice crystals. But in the warm clouds of the tropics, it's a chaotic, high-speed demolition derby. Let's just put them side by side to make it super clear. Yeah, this table lays it all out. On one side, you've got the Bergeron process. That's our cold cloud method, the one responsible for most of the rain in places like North America and Europe. And on the other side, you've got collision coalescence. That's the warm cloud champion, the king of the tropics. And it's all about pure physical impact. And here's where it gets really cool. In those massive, powerful thunderstorms, you don't have to choose. The 2 processes can actually team up. You get snowflakes forming way up high in the freezing cold tops. Then they fall and melt into already big raindrops. And then those big drops continue to fall through the warmer part of the cloud, getting even bigger by smashing into all the little droplets down there. This 1-2 punch, that's how you get the absolute heaviest, most intense downpours.
Speaking of intense, just how crazy can these rain-making engines get when they're running at full blast? Well, to answer that, let's take a look at the most extreme rainfall ever recorded on our planet.
All right, get ready for this number. In one single year, just 12 months, one spot on Earth got 2,647 centimeters of rain. I mean, that number is so big, it's hard to even wrap your head around what it means. So let's try to put that into perspective. That's over 86 feet of water. 86 feet. Picture a building that's almost 9 stories tall. Now imagine that much rain falling in one place. That's what happened in Cherrapunji, India. It's all thanks to the monsoon winds, just relentlessly slamming into mountains, forcing the air up, and supercharging these rain-making processes, day after day after day. So, the next time you find yourself watching the rain come down, maybe you'll just pause for a second, and you'll look up at those clouds and wonder, which story is this? Is this the story of a tropical collision, or am I feeling the melted ghosts of a snowstorm that happened miles and miles above my head?